Okay, so today's class, we are going to continue on module 3. We've been talking about charge carriers in semiconductors. Start off with talking about silicon bonding, the energy band models, charge carriers, electrons, and holes. We talked about intrinsic versus extrinsic semiconductors, and then we got into how to calculate carrier concentrations last time. I'm going to briefly cover that and then go on to talk about intrinsic and extrinsic carrier concentrations today, temperature dependence, and we'll start off with the density of states. Okay, hoping to get through, we'll definitely get through all this today, hoping to get into some of the drift currents, talking about what drift current is, getting into concepts of scattering, mobility, conductivity, velocity saturation, and so on. Okay, so last time we talked about the Fermi-Dirac function. Okay, can anyone tell me what the Fermi-Dirac function tells us?
The probability of finding electrons in either or the probability of finding electrons in the conduction band and the probability of finding holes in the valence band.
Yep, absolutely. Yep, the Fermi-Dirac function tells us the probability of finding, actually even more generally, like at any energy that we specify. The Fermi-Dirac function, you put an energy in, and then the output of the function tells you the probability of finding an electron at that particular energy. Okay, so and that function is used, as Melvin said, to find the electron concentration in the conduction band and the hole concentration in the valence band. Okay, to find carrier concentrations, we need to combine the Fermi function with density of states, and that's what I want to get to today. So what I'd like to start off with, though, just rehash the Fermi function real quick, and then we'll do an example problem. Okay, so when we're doing carrier concentrations, the way that I like to think about it, just a tongue-in-cheek kind of example, is that we think about a parking lot, and we think about the cars in the parking lot representing electrons, and we think about the parking spaces representing empty states. Okay, so an electron can, electron can occupy the empty state if the car is parked there, or the state can be left empty. Okay, an empty state would be considered a hole, and then a filled state, an electron in a state would be considered an occupied state. Okay, and the way that the energy, the Fermi-Dirac function kind of plays into this is we think about, if you look at this picture, you see that the more cars are parked close to the bottom end. That's because the building, we made the example of Costco wholesale, the cars like to be parked closer to the building because that is the lowest energy state. A person would expend the least energy walking to the building if they park their car close. Okay, so we can think about this as being an order of increasing energy. Okay, as you go to higher and higher energy states, you can see that more of the states are unoccupied. And by the time you get up to this side of the parking lot, well, it's mostly empty. Okay, the Fermi function, as we defined last time, is the 50% point. Okay, it's at the level of energy at which finding a car in a parking spot is 50%, or finding an electron in an energy state is 50%. Okay, all right, so the Fermi function looks something like this. At 0 Kelvin, the probability of finding an electron above the Fermi level is basically 0. The probability of finding an electron below the Fermi level at an energy state below the Fermi level is 100%. Sharp cutoff. Okay, but at non-zero temperatures, at higher temperatures, this function looks more gradual. It's a gradual transition. Okay, so it looks like a sigmoidal kind of curve. And the mathematical function describing that sigmoidal curve is given here. Okay, 1 over 1 plus e to the e minus ef over kt. Okay, so We talked about like what the Fermi function looks like in intrinsic N-type and P-type semiconductors. In intrinsic semiconductors, the Fermi level is right in between EC and EV. In the N-type semiconductor, the Fermi level is close to EC, far away from EV. And then in a P-type semiconductor, it's the opposite. The Fermi level is close to the EV, the valence band, far away from EC, the conduction band. In the case of the N-type semiconductor, what this means is that there's a higher probability of finding electrons in the conduction band, low probability of finding holes in the valence band. So you get a high electron concentration, low hole concentration. Vice versa in the P-type semiconductor, when the Fermi level is close to the valence band, you get a lot of holes in the valence band, very few electrons in the conduction band. Okay, so let's start off with this example today. Melvin, you have a question. Go ahead.
Yeah, actually, it was about the Fermi levels. 2 slides back, I think. Yes. So we have a Fermi level that's really close to the conduction band, and these are donors. So when looking at our Fermi level, it's kind of like, you know, transposed and kind of rotated on the left-hand side here. But you know, we have our band gap. Does that mean that we have a high likelihood of finding electrons in this band gap as well? The space between the Fermi level and the top of the valence band?
Very, very good question. Melvin's question was, do we have a high probability of finding an electron in the band gap? Right? Did I understand your question correctly, Melvin?
Yes, given just based on the Fermi level.
Yeah, excellent question. Like the way that we think about the Fermi level is below the Fermi level, like the Fermi function goes to 1. So there's a high probability of finding an electron below the Fermi level, right? So, but here's the thing. Whether you have an electron, you need to have 2 things. You need to have an empty state, and then you need that empty state to be full. You have to have a state available first, and then the Fermi function tells us whether that state is full or not.
I see.
Okay. So the fact is, in the band gap, we don't have states.
Okay. Understood.
So if we want to figure out what the carrier concentration is, which is what you're getting at, Melvin, there's 2 questions we have to ask. We have to ask how many available states are there? That's the density of states. We're going to talk about that today. And then what is the likelihood that that state is occupied? That's the Fermi-Dirac distribution. So we talked about this one already.
So in this case, we ask these questions to ourselves kind of sequentially. We say, if there are available states, then we can use the Fermi-Dirac function. But if there are no available states, then the Fermi-Dirac function is pretty much holds no weight.
Hang with me here, Melvin. We will get to that today. Again, very good question. Your question is whether we consider this sequentially or not. Actually, what we're going to find is that we multiply these 2 things together. We multiply the density of states with the Fermi-Dirac distribution.
Gotcha. Okay, Thank you.
Thank you. All right. So we're going to start off with this example today. Okay. This will help you on the homeworks. And it's just a quick calculation. Just go ahead and try this. Take out a sheet of paper, break out your calculators, and let's try this question. What is the probability of finding an electron at an energy 0.3 electron volts above the Fermi level? Okay, so try that problem first. I'll give you a few minutes to do that. 4 minutes. And if you're done with that, then you can go ahead and try the second one. What is the probability of finding a hole at an energy state 0.3 electron volts below the Fermi level? Okay, and then what do you notice about these probabilities? So I'd like everyone to just go ahead and try that on your own. I will mute myself for a few minutes.
For the temperature, are we assuming
Yep. Assume room temperature for these problems.
Okay.
I'll give everybody a little bit of a hint here. You're going to see that the Fermi function has this thing kT. Okay. And K is the Boltzmann constant and T is the temperature. If you multiply those 2 out in MKS units, you will find that KT is equal to 0.026 millivolts at 300 Kelvin. Okay, good rule of thumb to remember for this class, not just for this module, but for the entire, entire class. K times T is equal to 0.026 millivolts. Oh, my mistake. Electron volts, not millivolts. KT over Q is in millivolts. We'll get to that. We'll talk about that later. 0.026 electron volts. All right. So any luck so far?
Me, I got 9.28 times 10 to the negative 6. Is that
Okay.
right?
Let's go through it real quick. 9.28 times 10 to the negative 6. All right. So I'm going to do, let's call this part A, and we'll call this part B. So we'll do part A down here. So the probability of finding an electron, Ali, you can help me out here, is equal to 1
over 1
plus
E
exponential of
minus F
E minus EF
over KT.
over KT, yep.
So for E minus EF, I put 0.3.
Yeah, that's the key step here. So students often ask me, well, you told me that the energy is 0.3 of electron volts above the Fermi level. What is E then? We don't know what E is. We only know what E minus EF is, okay? So this is where you plug in your 0.3 electron volts here, okay? And then your KT, Ali, is?
For K, 8.63 times 10 to the negative 5. 300.
Yep. And what did you get for KT, the product?
I just multiplied like one time.
Got it. Okay. There's a little shortcut you can use here. You can just, at KT at room temperature at 300 Kelvin is equal to 0.026. Right, and that shortcut is helpful because now you just have an exponential 0.3 electron volts at the top, 0.026 electron volts in the bottom, numerator, denominator here. So the electron volts cancel. You just end up with 0.3 divided by 0.026. So it kind of simplifies the calculation a little bit. Ali, can you help me out here? What do we get here at the end?
I got 9.28 times 10 to the negative 6.
Times 10 to the negative 6?
Yeah.
Okay, do anyone else agree with that? Do we have agreement?
I got the same as well.
Okay, great. Okay, so that's part A. Part B, so that means there's a 9.28 times 10 to the negative 6 probability of finding an electron at energy state, 0.3 electron volts above the Fermi level. And part B, we have to find the probability of finding a hole at an energy state 0.3 electron volts below the Fermi level. So the probability of finding a hole is 1 minus the probability of finding an electron at 0.3 eV below the Fermi level. Okay, so in this case, the probability of finding an electron is the same thing as before, except this portion here, the E minus EF, so here you're going to put, because the Fermi level is below, and because the energy is below the Fermi level, this portion here, you're actually going to put negative 0.3. Okay, instead of positive 0.3. And then the denominator will still be 0.026. Okay, and without going through all the math here, you'll find that this is the same as this. Okay. So this has to do with the symmetry of the Fermi function. Okay. So I'll let you, kind of look at that on your own and discover that on your own. Okay. All right. So moving on then. So we figured out the first part of the puzzle. The Fermi-Dirac distribution tells us the probability that a state is occupied or whether it's empty. So the next piece of the puzzle is whether we have a state at all. As Melvin pointed out earlier in the class today, excuse me, the band gap, within the band gap, there are no energy states, right? So we have to take that into account. Let's just go back here. So here within the band gap, right, you have EC, EV in between them. In between them, you don't have any states. Okay, that's the whole definition of a semiconductor, is that you have a region of energies where there are no available energy states. Now what we're going to find out here is just a little bit more of an understanding of what we knew before. Our understanding before was that there's a whole bunch of energy states above EC, a whole bunch of energy states below EV. But in between, there's 0 states. Okay. So the second part doesn't change. There's 0 states between EC and EV. But above EC, it doesn't just go to a high number of states immediately. It actually transitions. What does that mean? It means that above EC, right at EC, there's still very few, there's 0 states right at EC. But once you go above EC, the density of states starts to increase as you're going higher and higher in energy. Okay, I'll say that again. EC, there's actually no energy states right at EC. As you go above EC, then the density of states increases like this. Okay. And the density of states, the way that you can kind of think about it is, remember, each line that you draw on one of these graphs represents an energy state or an orbital where there's 2 electrons can occupy that orbital. So instead of being something like this, where there's a whole bunch of energy states at equal density, it actually goes something like this. There's 0 states there. There's a low density of states here. As you go higher and higher and higher, there's more and more density of states. So more and more states per electron volt, you can think about it. And the way it's described is with this function here, or this one, either one. Let's both are saying the same thing, okay? But let's start off by looking at this graph here. So this is the energy, and this is N of E, which represents the density of states. Okay, so you can kind of think about this as being the conduction band. At the conduction band, there are 0 density of states. As you go above the conduction band, the density of states increases like this. And this turns out to be like a square root function. Okay, it increases as a function of the square root of the energy. Okay, so if you take this graph here, flip it 90 degrees, you'll get something like this. Okay, this one, for some reason, I always found as a little bit confusing to read here. But this axis is showing the density of states. This axis is showing the energy. It's showing the same information as in this graph. So it's saying that at EC, the density of states is 0. As you go higher above EC, the density of states increases. And it increases as a square root function. The same thing happens down in EV. There's a low density of states right at EV, actually 0, and then it increases as you go lower and lower and lower. Okay, so that's represented by this graph here. Okay, so we're not going to derive the exact formula for N of E. It's something that can be derived with quantum mechanics, and it's beyond the scope of this class. What we will kind of want you to know in this class is in a 3-dimensional material like silicon, is that this N of E is proportional to E to the 1/2, meaning it increases as a square root of the energy. Now, this is complicated, right? We would like to simplify this by kind of making an approximation. Instead of, we don't like to have a varying number of density of states as we go higher and higher in energy. That means if we want to do any kind of calculation with this, we have to involve integrals. And integrals just complicates things. We already have enough stuff to deal with the Fermi-Dirac distribution and other things. So it turns out we can do a bit of a shortcut. We can kind of assume that the density of states is constant. We assume that it's a constant. And I know it sounds kind of weird because at the beginning I just said it's not constant, and now I'm saying we're assuming it's a constant. It's an engineering approximation. So if we want to approximate this blue line here like this, we kind of just draw a line kind of like this that approximates the average value of this blue line. Okay, and this average value is given by this N sub C and N sub V. Okay, so these are approximations. So this is the density of states in the conduction band, and this one here is the density of states in the valence band. So, and this is called, I just want to say this is called the effective density of states, just to reflect the fact that it's an approximation. The actual density of states varies as a function of energy. This one is just a constant value. Okay, so let's look at what's in this formula. 2 pi mn star. This is something called an effective mass. We have this KT factor, and then Planck's constant squared at the bottom. This is for density of states in the conduction band. For density of states in the valence band, the Mn star is replaced with MP star. The MP star is an effective mass for holes. We'll get to that later in this module. Okay, so now that we know the Fermi-Dirac distribution and we know the effective density of states, the electron concentration is just the product of the two. Okay, we said at the beginning here when we determined carrier concentrations, we need to consider how many available states are there and what's the likelihood of finding a carrier in each of the energy states. The parking lot analogy is we count up the number of parking spaces, and then we kind of figure out the probability that each of the parking spaces are full. That's how we come up with an estimate of the total number of cars in the parking lot. In a semiconductor, we want to find out the number of electrons in the material. And more specifically, we want to find the density of electrons in the material. Density means how many electrons do we have per cubic centimeter of semiconductor material. And the more we have, the more conductive the material is. Okay, so the key thing is that we multiply. We multiply the effective density of states by the probability that the state is occupied. That's the Fermi function. Okay, since we know both of these now, we can plug in the formulas that we found on the last two slides. At the conduction band EC, the electron concentration is equal to N sub C. This is the effective density of states in the conduction band multiplied by the Fermi function at EC. So the Fermi function at EC is given by this equation, 1 over 1 plus E to the EC minus EF over KT. And so we now have a formula for the electron concentration in the conduction band. Similar formula for the valence band we can derive. Okay, all it is just a product. Effective density of states times the Fermi function. Okay, next. Instead of just thinking about this mathematical equation, it's always good to visualize, okay? Really emphasize that. So I want you to see what it looks like to multiply two functions together in this case. Okay, the carrier concentration is a product of the density of states in the Fermi function. And so that is what is shown here. This column here shows density of states, N of E. And this column here shows the Fermi function, F of E. Okay, and these are just showing the typical energy band diagrams. This is for an intrinsic semiconductor. This is for an N-type. This is for a P-type. So what you notice here, if you look at this graph, and there's a lot of information here, so just bear with me here. In the intrinsic semiconductor, as we saw before, the Fermi function is right in the middle. N-type semiconductor, the Fermi level is above the midpoint. It's closer to EC. And for a P-type, the Fermi level is closer to EV. So we know that already. Next thing we go is the density of states. So notice the density of states function is exactly the same for all of the semiconductors. The density of states does not change depending on dopant. Function is identical. 1, 2, 3. They're all the same. The Fermi function is what changes. So we start off with the intrinsic case. The Fermi level is positioned right in between EC and EV. Okay, now I want you to picture this. I want you to picture multiplying these functions with the Fermi function. So you have the density of states in the conduction band. Imagine multiplying this function with this function here. Okay, the density of states gets more and more and more as we go to higher energy states. But the probability of finding an electron at that energy state has already gone to 0, essentially. So even though there's a high density of states up here, it doesn't matter because all those states are empty. So if you, on the other hand, if you go right at EC, what you'll find out is that there's 0 states. There's a non-zero probability at EC. I'm going to zoom in here. The Fermi function tells us there's a non-zero probability, but there's no states. So again, the carrier concentration here is 0. And then up here, it's also 0. But in the middle, okay, just above EC, there are some states available, and there's also a non-zero probability. So as a result, there are electrons just above EC. So there's electron concentration above the conduction band, just above there. But if you go too far above, the electron concentration goes to 0. Okay, so what this is telling us is that most of the electrons, the electrons, which is one type of charge carrier in a semiconductor, they're hanging out right at the conduction band. If you repeat the same analysis for holes, you'll find that there are a bunch of holes hanging out in the valence band. What are some of the key points here? Right at EV, there's no states, but there's the probability of finding a hole is non-zero, because you can see that the Fermi function is close to 1, but not quite 1. Okay, so there's a probability, a non-zero probability of finding a hole, but no empty states. There's no available states, I'm sorry. As you go to lower energy, the density of states increases, the Fermi function goes towards 1, which means the probability of finding a hole is going towards 0. So again, you have a situation where there's holes just below EV, but there's, by the time you go too far below EV, that means all the states are basically full, and so there's no holes. So in intrinsic semiconductor, we've talked about this before already, you have some electron concentration up in the conduction band, some hole concentration in the valence band. Okay, just to remind everyone, this corresponds to this mental picture that you'll have up here. Okay, remember we said that in an intrinsic semiconductor, we have a situation where there's a few electrons that get bumped up into the conduction band. And when they do, they leave behind a hole. So there's an electron hole pair formed. So at any given time, there's a certain number of electrons and the same number of holes. So that is essentially what is being shown in this diagram here. So we had our energy band model, and then I showed you the physical model before. So I want you to have both pictures in your head. Okay. Now for an N-type semiconductor, the difference here is that the Fermi level is closer to the conduction band. Okay. So that region of non-zero probability extends upwards into the conduction band, extends further up into the conduction band. As a result, you have a larger chunk of electrons. Okay, where this is what your number of electrons look like up here. This is how your number of electrons looks here. There's a larger region of energies where the electrons can exist. So there's a higher electron concentration. This all basically came from moving the Fermi function, the Fermi level upwards. In the p-type, it's just the opposite. The Fermi level is lower, close to the valence band, and that increases the probability of finding a hole in the valence band. I also want to look what it does to the alternate carrier. If the Fermi function is close to the conduction band, large number of electrons, fewer number of holes. Okay, it's a subtle but important point. In the intrinsic semiconductor, you can see that the electron concentration and hole concentration basically are the same. They're created in pairs. And so this area here and this area here they're going to be equal to each other. In the case of an N-type semiconductor, these areas are no longer equal. you have a smaller hole concentration, larger electron concentration. And the hole concentration in the valence band is smaller compared to the intrinsic case. See the area here and the area here is, you can see that it's decreased as you went from the intrinsic to n-type. In the other case here, in p-type, p-type semiconductor, you can see many holes and few electrons. Okay, so good. I think we have a reasonable understanding of Fermi levels then. Let's talk about multiple dopants. And instead of just telling you what this is, I'll tell you, but I want to try to think about this as a mental exercise first. Okay. For this type of problem, conceptual question, you can think about it in terms of the energy band model. You can think about it in terms of the physical model. You can think about it in terms of both. This is what semiconductor researchers or engineers do. They think about some things in terms of the energy band model, some things in terms of the physical model. Okay, so let me know what felt more comfortable to you in this case. But I'm looking to see if you can reason this out. Question is as follows. Let's say we dope a semiconductor first with some concentration of acceptors, N sub A. Remember, an acceptor is a column 3 element. Whenever you have an acceptor that's doped into the lattice, the column 3 element replaces a silicon atom and it generates a hole or an incomplete bond. So you first dope with acceptors and then subsequently you dope it with donors. So this is a two-step doping process. This is referred to as multiple dopants. So the two questions are, what happens if ND is much greater than NA, meaning the donor density is much greater than the acceptor density? And second question is, what if ND is equal to NA, meaning like the donor density is the same as the acceptor density? So I'll let you think about that for a minute, and then I'll request your thoughts. Okay. Any thoughts?
Would the, I guess your EC become, like the density get larger if your ND was greater than NA?
What would get larger, Corey? Sorry, I missed that.
Sorry, the, I guess the, what is it called? The, like the carrier, or sorry, not the carrier concentration, but your
Carrier
EC
concentration?
value.
Mm-hmm.
Yeah. In the previous slide where you had kind of like your EC and then your electron density there, that would just grow that area.
This area up here?
Mm-hmm.
If you doped, are we doing the acceptor doping first or the donor doping first?
Okay.
Well, let's start, let's do one step at a time. Let's start with the acceptor doping first. So what happens when you do the acceptor doping?
You create holes.
Yeah, that's right. You create you create this energy state in the valence band called E sub A. And then with just a little bit of energy, the electrons from EV go up to EA and they leave behind holes in the valence band. Now, the next step is, let's say we have donors now after that. So then we create this donor state, ED, up here. So from the donor state, a bunch of electrons go into the valence band. Now what's going to happen?
I mean, you're effectively decreasing your band gap length. Is that what's happening?
Good point. Good point. It's true. We are making the band gap effectively smaller. That is true. But let's not consider that for the time being. Let's just consider what's happening with the electrons and holes. So this is, I just want to, so nobody gets confused, this energy band diagram is showing the case where ND is much greater than NA. How do we know that? Well, you look at there's a dopant, the donor level up here, and then you see a whole bunch of electrons in the conduction band. But down here, you only see a few electrons in the valence band. Okay, so I'm kind of giving you a hint as to what the answer is going to be. I'm just kind of looking for reasoning, your reasoning.
So when you say that, what happens, are you asking what happens in terms of the
Carrier concentrations.
carrier concentrations? Oh, okay.
Yeah. So let me. Yeah, I think that's helpful to have on here. Okay, I'm going to make a little bit of space here because we have an energy band model up here. So this is the energy band model. We can also draw a physical model. So I think it might be useful if we think about that as well. Okay, so right now we are considering this first case, and we're going to draw the physical and energy band model for that first case. Okay. So this was ND is much greater than NA. So let me just restate. You can see there's a whole bunch of electrons up in the conduction band, only a handful of holes in the valence band. So this is a situation where ND is much greater than NA. What do you think will happen to these electrons up here? You have electrons up here, and then you have empty states down here.
Will they, I want to say they'll possibly recombine.
They will recombine. Yeah, they'll actually go back downwards to this this state. And actually, what could the actual model is a little bit more complicated than that. This guy actually takes a small step and goes to the lower energy state, and the higher energy electron then occupies the state that that the other one just left open. Okay, so I'll just draw that.
Is there a reason that the electrons in the conduction band jump all the way down to the empty state in the acceptor, I guess, band, rather than the empty states in the donor band that were just kind of left? Because the electrons in the acceptors, when they'll recombine, but recombine.
Yeah, that's an excellent question. The electrons could go back down to the donor state. So an electron could go back to down to the donor state here, but then it might still find a lower energy state and continue downwards.
Okay.
You see? Because remember, the basic rule is that electrons like to occupy at the lowest energy states that are available. So if an electron happens to see an open state way in the valence band, it's like, hey, that's a much lower energy state. I'd like to take that one. So the electron concentration that you created in the conduction band. Well, let's put it this way. We first doped it with acceptors, right? When you first dope it with acceptors, you generate holes in the material. So there are your holes down here, okay? But by further subsequently doping it with donors, we're creating all these electrons in the conduction band. And those all those extra electrons are going to say, hey, you know, there's some empty states down here, so I'll just go and occupy those. And your holes, what happens to your holes then? You just go away. So you've effectively like turned your p-type semiconductor. When you doped it with Na, you had a p-type semiconductor. Now by doping it with Nd, you've turned it back into an n-type semiconductor. So let's do the physical model too, so you kind of understand this. Here, let's do silicon. Let's draw this out. Okay. So let's say I first dope it with acceptors. So doping it with acceptors means I'm going to take out this silicon, replace it with a column 3 element, so with boron. And the result of boron, because it has one less electron, it will create an incomplete bond or an empty state. So there's a hole here. Okay. Now let's say I dope it with donors. Okay. By the way, there's going to be more than one boron atom in there. I just drew one. But I want to reiterate the point that it's going to be mostly, whenever we dope, it's going to be mostly silicon atoms with just a few boron atoms scattered here and there. Let's say we now dope it with donors. Okay, so this one goes away. So let's say we have a phosphorus in there instead. So remember, phosphorus is a column 5 element, so it brings an extra electron into the mix. Okay, so in the physical model, the point I want you to see here is, what do you think is going to happen when this electron sees this unoccupied state? It's the same thing as the energy band model.
You know, recombine, or I guess combine, because they would never really.
It'll occupy. Yeah. We'll get to the term recombination we're going to cover in the next module, but yeah, it's the electron is going to recombine, meaning the electron basically sees, hey, there's an available energy state there. I'm just going to pop into that state because that's the lower energy state than where I'm at right now. This extra electron, remember, this extra electron is equivalent to an electron in the conduction band. It's at a high energy anti-bonding state, so it's free to kind of hop around the lattice. But if it sees a lower energy state nearby, well, there you go. It's going to just occupy that. Then the hole disappears, the electron disappears. So at that point, the dopant is neutralized. Now, if I have an additional phosphorus atom still, let's say I put another phosphorus atom in there. Now there's another extra electron. So this one kind of recombined, but this one doesn't have anywhere to recombine. So now the material has turned into an N-type material. Any questions? Okay. So the next question is, what if the column 5 density, the acceptor density is equal to the donor density? What do you think will happen then if they're exactly equal to each other?
Would you get something similar to like an intrinsic semiconductor?
Yes. There you go. Excellent. Very good. You'd end up getting something that looks like an intrinsic semiconductor. Good. All right. So these things that we just reasoned out logically is basically summarized by this equation here. It's a space charge neutrality equation. You'll be using this equation in one of your homework problems. This basically says for a material to remain electrostatically neutral, the positive charges have to equal the negative charges. Now, what do we mean by that? This is a hole. So the hole has a net positive charge. The electron has a net negative charge, okay? Now, let's talk about these terms here. Subtle but important point is that Nd is the donor atoms, okay? Now, if we go back to a picture of what the dopants look like. So this is a donor, arsenic, okay? So arsenic has a certain number of protons in its nucleus. And then it has a corresponding number of electrons. The number of electrons is equal to the number of protons. All right? So when arsenic bonds into the lattice here like this, because it has this electron, you know, it uses three of its outer shell electrons to form, or four of its outer shell electrons to form a bond. And then it has this one extra one that's left over. This electron might move somewhere else. Now, when this electron leaves the vicinity of the arsenic ends up having a net positive charge with it, associated with it. Why? Because, well, the arsenic, you know, when the arsenic atom was put into the lattice, it had the same number of protons and electrons. But if one of those electrons that it put into the lattice, if that thing moves away, now the nucleus has one effective positive charge, effectively a positive one charge associated with it, one extra proton. So this is positively charged material, positively charged atom. And if we go back to this, then every dopant that you put in there has an effective positive charge. Okay, so we call this a dopant ion. The holes have a net positive charge. The dopant ion has a net positive charge. Similarly, the acceptors, also a dopant ion, has a net negative charge associated with it. How do we look at that? Just go back to the diagram here. Every boron atom has an incomplete bond. Okay, and if this incomplete bond moves somewhere else in the lattice, then this boron atom is left with a net negative charge in the nucleus, meaning it has one less proton compared to what it had on its own when it's electrostatically neutral. Okay. So if you have situations where one dopant type is much greater than the other dopant type, you will see that this equation will simplify. And I'm not going to tell you exactly how, because that's in the homework problem. Okay, but if you have a situation where ND is kind of close to NA, a little bit greater than, but not much greater than, then you have to use this equation to figure out what the electron and hole concentrations are. Okay, you put in ND and NA, and that will help you figure out the P0 and N0. Just a definition, reversal is where an N-type material is made into a P-type material by adding more acceptors so that NA is much greater than ND. So the reverse is also true. You could have ND much greater than NA to make a P-type, to make Oh, I have a typo here. Sorry about that. By adding more, no, that's right. An N-type material can be made P-type by adding more acceptors. So Na is greater than Nd. Reverse is also true. A P-type material can be made N-type by having Nd greater than Na. Okay. Any questions now before we go on to the next next topic here? All right, good. Next important concept. The product of carriers and holes is a constant. Okay. Just remember this. This equation here, NP equals Ni squared. N0 P0 is equal to Ni squared. Okay, these two slides are basically talking about this. I'm gonna, even though this equation is highlighted already, I'm gonna circle it again, because this is a very important equation for the purposes of this class. Important for intuition. We already know this fact about intrinsic carrier concentrations in our head. Our intuition is that the electrons and holes are going to be, the concentrations are going to be the same. Why is that? Why are the electrons and hole concentrations going to be the same in an intrinsic material? We talked about this in class last time and even a little bit today. Intrinsic means undoped. Okay, I can see there's a little bit of, there's some confusion here. So talk to me, tell me what the confusion is about. Or I can repeat the question. Would that help?
Yeah.
Yeah.
Okay, so repeating the question, we already know that the electron and hole concentration are equal to each other in an intrinsic material. Why is that?
Aren't they just formed together?
Yeah, they're formed together. They're created in pairs. Exactly. So, I mean, it's something it's an intuition we already have in our head. N is equal to, Ni is equal to Pi. That's the thing up here. But what we're going to find out here is that N times P is equal to Ni squared. It's equal to a constant. Okay, what this means is that I like to think about it as kind of like a seesaw. Okay, so, you know, that's what an equation says. When two things are inversely related to each other, this is what it looks like. If you increase the electron concentration, then the hole concentration goes down. If you increase the hole concentration, electron concentration goes down. Okay. You could also have the situation where the electron and hole concentration are equal to each other. And that is the case of an intrinsic semiconductor. Okay, so some of the stuff we've been discussing in the last few slides. So this is an important relationship that you're going to be using over and over again. NP equals Ni squared, and Ni for silicon at room temperature equal to 1.5 times 10 to the 10 per centimeter cubed. Okay, this will be in the notes as well, but I'm just putting it out here. So N times P is a constant. Let's see where this formula comes from. Product of electron hole concentration is a constant in a given material and temperature. So here's the derivation. Previously, we calculated the carrier concentrations by multiplying the density of states in the valence and the conduction band with the Fermi function. So this is in the conduction band, the electron concentration in the conduction band is equal to the density of states multiplied by the Fermi function. Here you have the whole concentration, density of states in the valence band multiplied by the Fermi function. Now, if we multiply, if we multiply N0 and P0 together, we take this and multiply this together, okay? So we're multiplying the electron and hole concentration together. We're gonna see that we get a result that's only dependent on the band gap and temperature. So let's multiply these two things together. N0 times P0 is equal to this thing here, multiplied by this thing here. So we have a constant NC, we have a constant NV, and then we have exponential terms. Okay. When you have exponential terms like this, you know, exponential to the power of A times exponential to the power of B is equal to exponential of A plus B, right? So that's where this simple derivation comes from. We have two exponentials here, right? So we just add up, this becomes a single exponential, and we add up these two terms. So this is EC minus EF over KT. This is EF minus EV over KT. When we add these up, the EF actually disappears. And you're left with just EC minus EV over KT. So why is this result interesting? Well, EC minus EV is just the band gap. Okay, so it just becomes EG over KT. So NC is a constant. NV is a constant. The band gap is a constant for a particular material. And then this is just a temperature dependent thing. So this whole thing for a specific material and a specific temperature, N0 and P0 is going to be equal to a constant. This slide just continues on that idea because we're adding to it our knowledge that the electron and hole concentrations are equal to each other in an intrinsic semiconductor. So we use that knowledge now and we say NI equals NC, the same thing that we derived on the previous slide here. And because Ni and Pi are equal to each other, this is the same thing as Ni times Ni. So this is Ni squared. And then we come up with an equation for N sub I. Okay, the intrinsic carrier concentration is equal to the square root of these two constants, exponential of Eg over 2 kT. So it's dependent on the band gap and it's dependent on the temperature. Okay, now that we look at this equation, I want you to think back to our intuition of intrinsic carrier concentration. Okay, suppose we have a material with a super small band gap. So Eg is small. And then we have another material with a very large band gap. All right, so I want you to see how that's going to play out in the equation. If you have a large band gap, this term here, you're going to have a large negative exponential, e to the negative, a large number here. What's that going to do to the Ni? Exponential to a large negative number. How will that affect Ni?
0, somewhere close.
It'll bring it down. It'll reduce it. So increasing the band gap, if you have a large band gap, that's going to exponentially bring down the intrinsic carrier concentration. And that's something we already know because we talked about that at the beginning of this module. Like small band gaps, you're more likely to have carriers. Large band gaps, they're more conductive. They have fewer carriers. Okay, so we just derived that relationship here. This is an equation for the intrinsic carrier concentration, and this is an equation. This is the one that you're going to be using a lot. NP equals Ni squared. Okay. So this next slide, I hope will give you a little bit of intuition on the carrier concentrations versus the Fermi level. So we have these equations here. Now, what is the purpose of this slide? So it's going to be, you'll see it's going to become very useful for your homework problems. So in your homework problems, you'll usually be given n sub I. Okay, as I mentioned, n sub I for silicon at room temperature is 1.5 times 10 to the 10. And that's a constant that we're going to be using a lot. So this n sub I is a little bit easier to deal with than calculating NC and n sub V. The homework questions that you're going to be getting is that you're going to be asked to calculate the electron concentration and the hole concentration. So all we're saying here is that n sub C and n sub V, you can find those as well. But these equations, it's a little bit easier to deal with this form of the equation, the n sub I form of the equation, rather than the one that has n sub C. They're both interchangeable, as you've seen here. Okay, so these are going to be the equations that you use to calculate the electron and hole concentration. There's two forms of each equation. So if we look at the electron concentration here, the electron concentration is equal to n sub I e to the EF minus EI over KT. Okay, so you can see that the electron concentration depends greatly on the position of the Fermi level relative to the intrinsic level. Okay, this is a new concept that I'm going to introduce here. EI is the intrinsic Fermi level. And the intrinsic Fermi level is basically halfway in between EC and EV. So if this is our band structure, this is EC and then this is EV. EI is right in the middle. So in silicon, the distance between EC and EV is 1.12 electron volts. So the distance between EC and EI is half of that. So 0.56 electron volts. It's 0.56 electron volts below E sub C, 0.56 electron volts above E sub V. Okay, so you look at where your Fermi level is in relation to E sub I. And then you divide by KT. KT is equal to 0.026 electron volts at room temperature. So there's two types of problems you'll be given in the homework. One type of problem is where you'll be given the energy band diagram and you'll be asked to calculate the electron concentration. So in that case, you use this formula here. The other type of situation is where I will give you the doping and you'll figure out the electron concentration. And from there, you draw the energy band diagram. So for those types of situations, this form of the equation would be easier to use. Okay, both of these are, they're the same equation. You're just rearranging terms here. Okay, there's another equation similarly for the hole concentration. And notice this is EI minus EF instead of EF minus EI. This is a visual just to show you that moving EF, the position of EF causes an exponential change in the carrier concentrations. So if we look at, if the Fermi level were positioned right at E sub I, then the electron and hole concentration would both be equal to N sub I, 1.5 times 10 to the 10. This graph is showing the position of the Fermi level versus the electron concentration. So for an N-type semiconductor, if notice that as we linearly increase the position of the Fermi level like this, Okay, as the Fermi level moves higher and higher and higher, the carrier concentration increases by orders of magnitude in a log scale. Okay, so that means there's an exponential increase in the number of carriers as we're moving the position of the Fermi level. The closer the Fermi level is to E sub c, the more n-type it is. The lower the Fermi level is below E sub I, or closer it is to E sub v, the more p-type it is. Okay. The reason this is important is just by looking at the Fermi level in an energy band diagram, you should be able to tell me if it's n-type or p-type. You should be able to calculate the carrier concentrations. Okay, some units and constants to remember. I've given you this before. You have the K and the Qs. 1 electron volt is equal to 1.6 times 10 to the negative 19 joules. KT over Q. This is something that we use later in the term, is equal to 0.026 volts. KT, which is what we're using here, is equal to 0.026 electron volts at 300 Kelvin at room temperature. So with that, I'd like everyone to try this problem now. You'll have a very similar problem in the homework. These are the types of problems you're going to be doing over and over and over again in this term. So it's good that you get used to it now. So suppose we have an energy band diagram of silicon, and you suppose that the Fermi level is 0.3 electron volts above the intrinsic level. What is the electron and hole concentration? What is the doping, and what type of semiconductor is this? So I'm going to give you some time to do this problem. So I'll start you off by basically putting this on here. So with our energy band diagrams, we can draw our E sub C, E sub V. Then we can also draw our E sub I, the intrinsic level. And so this is saying that the Fermi level is 0.3 electron volts above the intrinsic level. And just to give everyone a sense of scale here, remember this distance is 0.56 electron volts. This distance here is 1.12 electron volts for silicon. Okay. So this problem is saying that the Fermi level is positioned 0.3 volts above the intrinsic level. So let's say it's right about here, 0.3 electron volts. So this is the position of the Fermi level here. Okay, so essentially I've given you the energy band diagram, and the problem is requesting that you figure out the electron and hole concentration, calculate the electron and hole concentration. And from there, you can figure out the doping. So I'm going to give you 5 minutes to do this, and then we'll discuss. And if someone finishes it sooner than 5 minutes, then please go ahead and share with the rest of the class. If anyone needs me to go back to the previous slides so that you can see some of the equations, I'm happy to do that. Just let me know when to do that. Yeah, you might want to copy this down in your page first.
What was n sub I, 1.5 times 10 to the 10th?
I'll put that here. Yep. N sub I equals 1.5 times 10 to the 10. And the units is per centimeter cubed. This is for silicon at 300 Kelvin, which is room temperature. Okay, let me know whenever we have, if anyone has it figured out. All right, any thoughts?
For the electron concentration, I have 1.54 times 10 to the 15th over centimeters cubed.
Okay. Let's go over your steps. Oops. Okay, so let's figure out n. So n sub 0. What is the equation that you used here?
0.3 equals kt natural log of n sub 0 over n sub I.
Oh, interesting. Okay, yeah, actually, you don't necessarily, if you're given the energy band diagram and you're trying to find out the electron concentration, you're actually better off using this first form of the equation. So you're suggesting use this one, which is fine. You could also use that as well. But it may be easier to use this one. When you're given the energy band diagram and you want to find out the electron concentration, go for this one.
Yeah, I guess that makes sense.
So n0 is equal to ni exponential of EF minus EI over KT. Okay, so I just want to see, it's just a real quick calculation. 1.5 times 10 to the 10. And the units is per centimeter cubed, remember? And then, so this becomes an exponential of EF minus EI. So EF is positioned 0.3 electron volts above E sub I. So this becomes 0.3 electron volts divided by KT is 0.026 electron volts at room temperature. All right. So let me do the math here. Someone can help me out here. Otherwise, I'll do it. Calculator.
It's 1.6 times 10 to the 15th.
1.6 times 10 to the 15th. Okay. I just want to go through one step here, 0.3 divided by 0.026. So this becomes exponential of 1.153. Oh, wait, I didn't do that right. 0.3 divided by 0.026, 11. I know I'm like belaboring the math here, but I just want you to see a little bit about how the different terms play out so that you have an intuition of the equation. So this position here, it says 0.3 electron volts divided by 0.026 electron volts. This becomes an exponential of 11.5. Okay, so this becomes 1.5 times 10 to the 10 per centimeter cubed times exponential of 11.5. So if we do the exponential of 11.5. I want you to see that this is a huge number here. So 98. 9.87 times 10 to the fourth. Okay, so the reason I'm belaboring this is so you can see that the position of the Fermi level determines the exponential, and this exponential will greatly, this will basically be a multiplier for the intrinsic carrier concentration. The intrinsic carrier concentration will get multiplied up by this exponential term. The farther EF is away from EI, that carrier concentration will go up very rapidly. And Janan, what did you get for that then? I think you're on the right track there.
1.6 times 10 to the 15.
Okay. 0.6 times 10 to the 15th. Okay. And the units are per centimeter cubed. All right. Now, the whole concentration, once you know the electron concentration, you use NP equals NI squared to find the whole concentration. Okay, this is a shortcut, right? Well, not a shortcut. You could use the same equation on the left to figure out the whole concentration as well, but this is much faster. So the whole concentration, once you know the electron concentration, you can find the whole concentration easily. So P0 is equal to Ni squared over N0. So this is 1.5 times 10 to the 10 squared over N0. The N0 is what we found earlier, 1.6 times 10 to the 15th. All right, so I will do that real quick. 1.5 times 10 to the 10 squared divided by 1.6 times 10 to the 15th. And we get a whole concentration of 1.4 times 10 to the 5 per centimeter cubed. Okay, so we have our whole concentration and our electron concentration. What do we notice here? Intrinsic carrier concentration is 1.5 times 10 to the 10, right? So that's what you would have in an undoped semiconductor. In our case, what do we have? Our electron concentration is 1.6 times 10 to the 15th, 5 orders of magnitude greater than the intrinsic carrier concentration. So the electron concentration has gone way up. And notice the whole concentration has gone in the other direction. The whole concentration has gone down compared to the intrinsic concentration. It's gone down from 1.5 times 10 to the 10 down to 1.4 times 10 to the 5th. Okay, so this is that seesaw effect. What type of doping is this? Is it N-type or P-type?
It would be N-type.
N-type, right? Because we have more electrons than we have holes. And then the last part here is, what is the doping? The doping concentration.
For what is the doping? The second question. That is that something we compute with a formula?
Yeah, actually,
Okay.
yeah. You know what? I mean, the formula is so simple, we almost don't need a formula for it. We have to think a little bit conceptually about it, but yeah, or it'll be very obvious to you. I'll just go ahead and do it because we're just about out of time here. So when we say doping, I just mean doping concentration. Okay, so I will say that the doping concentration is equal to this. So we're going to say that ND is equal to 1.6 times 10 to the 15th per centimeter cubed. Now, why did I just write that number down? Why does that make sense? The electron concentration in this material is 1.6 times 10 to the 15th. For every centimeter cubed of material, there's 1.6 times 10 to the 15th electrons. Now, every place where there's an electron, if you think about it, there has to be a dopant, an associated dopant. Right? Because there are conceptually, our mental model is this, is that for every column 5 element that we put in there, every arsenic, go back to this picture. Oops, not that one. For every arsenic or other column 5 element that we put in there, provided a single extra electron. So we've already calculated our electron concentration now. So we know that the concentration of dopants is the same as the concentration of electrons. So that's how we back out what the donor concentration was. Okay, so 1.6 times 10 to the 15th. Okay. And so this is an N-type semiconductor. I know we're at 7:10 right now. There's just one more concept I want to cover because I just don't want to fall too behind in the class. So I would appreciate if we could just stay like an extra like 3 or 4 minutes here. We'll just cover this slide real quick. This slide is showing the temperature dependence of an extrinsic semiconductor, a doped semiconductor. Right. Now, some of this stuff hopefully will seem obvious to you, or it'll make sense to you. But the beginning graph that I show you might not. So this is showing the electron concentration for an N-typed silicon doped with 10 to the 15th donors. Okay. The first thing you'll notice here is that the electron concentration, it depends on temperature. Initially, you might be thinking, why does it depend on temperature? But once you go through these different steps, I mean, it ties in exactly to the concepts that we talked about earlier. There's 3 regions here. The first is the ionization region. When you dope a semiconductor and you're at 0 Kelvin, remember when you dope it, you create this extra donor level here, so E sub D, and that is filled with electrons. At 0 Kelvin, there's not enough energy for these electrons to go up into the conduction band. So you don't have any electrons in the conduction band. We mentioned this in class last time, that a doped semiconductor at 0 Kelvin actually will not be conductive. If you start increasing the temperature to just above 0 Kelvin, even 50 Kelvin, you'll get to this portion of the map here. Even at 50 Kelvin, there's enough energy for all these electrons to jump into the conduction band. So at that point, what they say is that the dopant level is ionized, meaning all the electrons have gone into the conduction band. That happens at around 50 Kelvin. Once you're at 50 Kelvin, then the electron concentration stays the same for a large range of temperatures through here. This is what's called the extrinsic zone, which is at moderate temperatures. And this is where we use the doped semiconductor. We like to use the semiconductor in this zone. But what'll happen if we go to really high temperatures? What if you take a semiconductor and you push it even higher? Then it's going to go to this intrinsic zone. Can anyone tell me what might happen? Just from your understanding of energy band diagrams, what happens if we go to really high temperature? Think about this energy band diagram and what'll happen if you bump up the temperature really high.
You'd probably have too many electrons in the conduction band that it might be counterproductive.
And where are those electrons coming from? because the dopant level is already gone. All the electrons from here have already jumped up here. Where are those additional electrons coming from?
The lower band.
Exactly. And that's the point I wanted to get to, that these electrons from the valence band start to jump up. That's why this region is called the intrinsic region, because it starts behaving like an intrinsic semiconductor at high temperatures. So at high temperatures, the electrons from the valence band are going up into the conduction band. And at that point, it doesn't matter that it was doped or undoped. Like a lot of electrons are coming from the valence band. So the number of electrons in the conduction band just shoots way up. Okay, this is one of the fundamental limitations of semiconductors, why they can't be used at high temperatures. If you take silicon and you put it up to like, very high temperatures, like 400 Celsius or 600 Celsius, you're going to start to see this effect where the semiconductor becomes conductive everywhere, and basically it's shorted out. It's just conducting everywhere. So that's not really useful. When we build semiconductor electronics, like we want certain parts to be conductive, we want certain parts to be non-conductive. We want to be able to control the conductivity. So it's not really of use to us if it's always conducting. So we want to operate semiconductors in this zone, what's called the intrinsic zone. Okay. And this last graph here just shows that in a doped semiconductor, the Fermi level and carrier concentrations, they both change with temperature. I know we've talked about the Fermi level as being something independent of temperature, but it turns out that the Fermi level moves with the temperature. So if you have an N-type semiconductor, this graph, just take a look at it at home, because I don't want to, we're already over on class time here. If you have an intrinsic semiconductor, the Fermi level stays in place for all temperatures. Okay, the Fermi level stays in place. But if you have an N-type semiconductor with, say, doping of 10 to the 12th, at low temperatures, you'll see that the Fermi level is way up here. And at higher temperatures, the Fermi level starts to move down. And by the time you get to really high temperatures, significantly higher than room temperature, the Fermi level basically merges with the intrinsic level. Okay, and it's sort of showing this effect here. The fact that a semiconductor looks more and more like an intrinsic semiconductor as you go to higher temperatures. Okay, so low amounts of doping starts to look intrinsic just above room temperature. Higher doping, like 10 to the 16th or so, starts to look intrinsic at temperatures of 500 Kelvin, which is 200 Celsius. Okay, so just keep that in mind. All right. So thus far, to recap, we've looked at simplified energy band diagrams of N-type and P-type intrinsic semiconductors. We've calculated carrier concentrations. Now you know how to calculate carrier concentrations. You know how to draw energy band diagrams, and you know how to relate the two together. So next time in class, we're going to start looking at the behavior of carriers, how carriers move in the presence of electromagnetic fields, and basically how you get electrical current. There's a bunch of things that goes into play. First is the whole concept of drift current. There's the concepts of mobility, scattering mechanisms. We'll derive conductivity and Ohm's law. And basically, we're going to figure out how to make a semiconductor resistor. All right. So that's what's up for class on Wednesday. Thanks for staying a little bit extra today. It's just trying to make sure we don't get too far behind. Any questions before we end class today? Okay, good. Just a reminder is look for the homework solutions for Module 2 are going to be posted. Please look at those solutions, compare them to the results that you got on the quiz, and just start studying. This is a good way to just cover what you've already, cover what you missed, cover what you didn't get right, and it'll also help you in preparing for the exam that's coming up in a couple of weeks.
I have a question for you.
Sure.
More of a, I guess I'm just more so curious.
Mm-hmm.
A few slides ago, we were talking about the ionization, the extrinsic.
This one?
Yeah, as the temperature goes up,
mm-hmm.
If let's say But let's say if, as the temperature, let's say, approaches something like infinite, and we were saying that, you know, atoms, theoretically, they have an infinite amount of, you know, states that they can fill. Is it possible, similar to the photoelectric effect, that, you know, when you shine the light onto a certain material, it'll, apply enough energy to the material that it'll eject an electron from the material? Can heat also be a catalyst if you go high enough to eject?
Yeah, great question. Great question. Yeah, the answer is yes. I mean, like in principle, if you were to apply enough heat to a semiconductor material, you could potentially ionize an electron.
I see.
But, and here's the but, is that sometimes that temperature would be so high is that you'd end up melting the material before you got to that point.
I see. Okay.
So that's one of the reasons why, like, you know, Einstein's photoelectric experiments, they, you know, if he had to like go to really high temperatures, then first of all, melting it is slow. And even if you did get some kind of ionization, it wouldn't be done in a very controlled way, you know? Because when you increase temperature, the process is kind of messy, right? Like it's a stochastic process. You have electrons that are going to high energy states and then going back down to lower energy states. As you increase the temperature, it's creating a distribution of electrons at higher energy states. So it's not a very well-controlled way to apply a very specific energy to an electron. Einstein's experiment with the photoelectric effect was better because he applied a very specific wavelength of radiation to the metal, and he knew exactly what that energy it was. And then he could find out, like, at what energy did he start to knock off electrons from the material.
I got you.
Yeah. So good question, though. All right. So, okay, with no more questions, we'll end class here today. Thanks again for staying extra, and I'll see you on Wednesday.
Thank you, Professor.
Thank you.
Thank you.
Bye.
Bye.
Thanks.